Hi guys, welcome to this next video. We're going to carry on with chapter 2.4, and I just thought perhaps one of the best ways to get into this material is just to start off with an example, and in the example we'll discuss the theory and some of the concepts that are quite important. So the example that I chose is an example that's in your textbook. It looks like this. Example 2.6. Okay, so if you understand this very well, then I guess you don't need to do this example, but I just want to highlight some things going through this one. So you can follow in your textbook, you can look at this video. So the main thing here that we have is that we've got two forces, F1 and F2, and if you look at the figure, it says that there's a link is subjected to two forces, F1 and F2. And what we need to do is we need to determine the magnitude and the direction of the resultant force. Okay, so the way I like to basically teach is always to bring you from what you know already. So what we did in chapter 2.3 and 2.4 is if we have two forces here acting on an object, on a body, then what was the technique that you used? You used the parallelogram technique, right? If you recall, you would complete the parallelogram and then you would get some kind of resultant force there. Then you would determine the angles here and you would determine the magnitude using the cosine and the sine rule. Well, that is still valid. It's a perfectly valid technique to use. Chapter 2.4 speaks of another technique which we can use, which perhaps you've heard in the mainstream lecture is perhaps the simpler way to go about calculating resultant forces. And chapter 2.4 is on the addition of a system of coplanar forces. Okay, so the basic idea with this technique is that we resolve our forces into the x and y, into their x and y components. Then we add up all the x components, we add up all the y components, and then using the resultant x and y components, we calculate our final resultant. So let's have a look at how we would do this. Okay, so this F1, as you can see, is 600 Newton at 30 degrees to the horizontal, and F2 is 400 Newton at 45 degrees to the vertical. Okay, so how do we go about solving this problem? It's actually very simple. We start off by just saying that we choose, now we're going to work in the x direction, okay? We choose going to the right, this direction to be positive for the x direction, and we say the resultant force, Fr, refers to resultant force in the x direction, is equal to the sum, that's a sum of all the forces in the x direction. Okay, so what does this mean? It means the resultant force due to all these forces in the x direction is the sum of all the x components of these forces. Okay, so we'll see what happens now. So let's take a look at F1. F1 is 600, and this is an angle of 30 degrees. So how do you get the component in the x direction? Well, it would be this component here. And how would you do that? You would say, basically, F1 cos of that angle, 30. So that then equals 600 cos 30. Now take note that we said to the right is positive. So can you see that the component of this 600 is to the right? Which means that it has a positive value. Okay. So we've taken care of that component. Now what about this one? Well, we know that if we look at the component, it is going to the left-hand side. It's going to the opposite side of what we chose to be positive. So we need to say then minus 400 and that's 45 degrees, and you can see the angle is between that force vector and the vertical. So you've got some options. Because it's 45, you might even get away with saying cos 45 simply because it's 45. But actually what we're after is that component there, which is the same as that one, which will then be sine 45. Guys, and I really want to encourage you to please practice your trigonometry, practice being able to calculate your components using angles, using cos, sine, and tan. Please go practice that, go brush up on it. That's very important. Okay, then the resultant of this is 236,8 Newton. That means it's positive, which means that there is a component in the x direction of 236,8 Newton in the positive x direction. So you can either leave it like that, or the textbook also shows that you can draw an arrow. Okay, so 236 gives us the magnitude, and then the arrow, or even if there's just a positive here, it shows that it's going in the positive direction, but the arrow also shows us it's going in the positive direction of what we chose there. Now let's quickly do the vertical. FR, we choose up to be positive. Okay, so we say the resultant force in the y direction is equal to, what do we say? The sum of all the forces, all the components, the y components of the forces. The resultant force in the y direction is the sum of all the y components of the forces. Okay? So let's go to F1 again. What do you think it's going to be? It's going to be 600 sine of 30, because that's the component we're looking for. That is F1 sine 30. Okay? If you don't understand this, please, I encourage you again to please go and study this up. Okay? Then this one, what do we have here? We have, what is the component? There's our vertical component, our y component, and it is in the same direction as what we chose for positive. So it's going to be 400. And what is the answer? It's going to be cos, right? Cos. There's my hypotenuse, there's my resultant, and there's my 45-degree angle, so we're going to get a cos 45, and we end up with 582,8 Newton positive. Okay? So now we have our FRX and we have our FRY, which means let's draw this. Let's draw the vector diagram. We are going to have, there's my FRX, which is 236,8. And there's my FRY, which is 582,8. Okay. Then what is my resultant? There is the resultant. So by the way, can you see when I drew this diagram earlier, I was kind of relatively accurate. That if I'd used the parallelogram method, then I would have also gotten a resultant force in this direction. So here is the resultant based on the calculations. But now they want the magnitude and direction. How do we determine the magnitude? Well, FR is simply equal to FRX squared plus FRY squared square root, okay? Which is then equal to 236,8 squared, 582,8 squared. Get the square root, and then we get, the answer is then 629 Newton. Then if we're trying to calculate this angle, theta is then equal to tan to the minus 1 of opposite over adjacent. Opposite over adjacent, okay? Which is then 582,8 over 236,8. and that gives us 67.9 degrees. Okay, so there, I mean, this is a relatively straightforward example. There's your magnitude, there's our resultant in the x direction, there's our resultant in the y direction. Here is our force vector diagram, very helpful to do this. Please practice doing this. There is our FR, okay. There's the way we calculate our resultant force, 629, and that's the way we calculate our angle. So now we've got our magnitude and our direction, okay? So, pretty straightforward example. Practice it. Get all these basics right, because some of the problems become a bit more complicated. This guys, this is the first thing I wanted to mention, is that this is the scalar method, okay? So if you go and read in your textbook, this is the scalar method for solving this problem. I just want to briefly discuss the Cartesian vector method and why we want to use it. If you've done the Cartesian vector method, you may ask yourself, but it seems that the scalar method is simpler to do than the Cartesian vector method. But let's just go over it quickly, and then I will explain to you why this is extremely valuable. The Cartesian vector method, or rather notation, okay? All that it's saying is, let us represent these forces in vector notation. Right now, guys, these forces are in scalar notation. There's a 600, which is a scalar, a 400, which is a scalar, and then you've got some angles showing you the direction. But let us rather represent these forces, and all the forces that we calculate, let's represent them in vector notation. What does that mean? It means we need to represent them in terms of our unit vectors I, J, and K. All right, we haven't touched on K, which is the third axis, which is the Z axis, but let's represent them in terms of I and J. Okay, so F1, and I'm going to put a little bar on the top there, equals 600 cos 30 in the I direction plus 600 sine 30 in the J direction, Newton. Okay, guys, please, I encourage you, just trust me when I say this. You must practice representing vectors like this in Cartesian vector form. This becomes very important later on when we begin to multiply vectors using the dot product and the cross product. Okay, please learn to represent your forces in vector form. So this is in vector form. What does this mean? It means that this, let's draw this again because that looks pretty small. If we have our F1 here equal to 600 Newton. Okay, I hope you can see that. Let me try that again. F1 is 600 Newton. Okay, and there's an angle of 30 degrees here. This is in scalar form. We have a magnitude of 600 and we have an angle here. But if I want to represent this in Cartesian vector form, I need to write it in terms of unit vectors I and unit vector J. Okay? All this is saying is that this force, 600 Newton at 30 degrees, is represented by the component in the x direction, which is represented by the unit vector I, and the component in the y direction, represented by the unit vector J. Okay? So remember, 600 cos 30 is my x component. That's what I have there. And my I is simply my unit vector in the x direction. We will touch on unit vectors later in more detail. And J is my and then the vertical component is 600 sine 30 in the J direction. So vectorially, if I add up this vector and that vector, I will get this resultant vector. Okay, does that make sense? F2, what does F2 look like? F2 is going to be minus 400 sine 45i, and then it's going to be plus 400 cos 45j Newton. Okay, so I've represented this vector, I've represented this force as in Cartesian vector notation. Please practice this. Then, what happens if we want to get our resultant force? Then it's very straightforward. We simply add up the i's, which is 600 cos 30 minus 400 sine 45 in the I direction. And then we add up the vertical components, 600 sine 30 plus 400 cos 45 in the j direction. And so my FR is then equal to 236,8 I plus 582,8 J Newton. Okay, so this is to represent the resultant force in Cartesian vector form, and this is to represent the resultant force in scalar form. The magnitude is 629 and the angle is 67,9. This is to represent it in scalar form, scalar notation. This is to represent the resultant in Cartesian vector form. Now you may ask, why? Why do we want to do this? Again, in 2 dimensions, guys, in 2 dimensions, it does look to me that the scalar form might be easier, or it might be exactly the same. In 2 dimensions, the scalar form might be quicker than maybe in the vector form you have to write now an extra I and an extra J and whatever. But guys, listen, when it comes to 3 dimensions, okay, 3D, 3 dimensions, when we have vector multiplication, the dot product, the cross product, it is imperative that you learn to write your vectors, your forces, in Cartesian vector form, because it might only be possible to do vector multiplication when you have your forces in this format. Okay, so please practice this. Learn to write your forces in Cartesian vector form. You still need to be able to do this, of course, but learn to write it in this form. Learn to add them up, because later we, especially section 2.7 onwards, we are going to be doing vector multiplication, the dot product, cross product. Even chapter 4, we're going to do the cross product, and it's crucial that we learn this method. Okay, well, I hope this helps. Thanks, guys. Cheers.